Okay, I will share the screen. Yeah. So, okay. Good morning to everyone who is present, and also to those who are going to join. All right. So we will continue with the examples. So we had seen a few examples, few classes of examples, and the birth-death chains with the two boundaries. That slide was the last one in the previous class. Today we will consider some more, some of which will be fairly specific type of example. What has happened? So here, two-state Markov chain. In some sense, this is the simplest form of Markov chain with two states. So it's the state space is a 2-point set, and generally we denote that by 0, 1. Of course, sometimes 1 and 2 might also be used. Here 0, 1, I mean 0, 1 in for perhaps some of this setup we are going to talk about. It's more convenient to use. So let P and Q be two numbers, real numbers between 0 and 1. Of course, P or Q equal to 0 or 1 is not ruled out. I mean, it is actually ruled out because both of them should be positive, strictly positive. Yeah.
When did the class start?
Pardon?
When did the class start?
Just about a minute back.
Okay, okay.
This is the first slide.
Okay, okay. I got confused.
Okay, first slide of today. Okay. So let P be given by 2 cross 2 matrix, this stochastic matrix. So that is 1 minus P and P in the first row, Q and 1 minus Q in the second row. So it's a stochastic matrix, and you can easily see that P00 is 1 minus P and P10 is Q and things like that. Note it down. So we will consider two kind of situations where such a Markov chain with this P can arise as the transition probability matrix. Of course, here that word probability is missing, transition probability matrix. So you can perhaps fill in that. Okay, first situation. Let us say a machine can be either broken down or be in working condition. So one considers the status of the machine at the start or the beginning of any particular day. So if it is broken down at the beginning of a particular day, then at that day it is supposed to be in state 0. If it is in working condition, it is in state 1. Clear enough? And also assume that if the machine is broken down at the beginning of the day, there is a probability P that it will get repaired and be restored to working condition at the start of next day. During that day, the repair work could be carried out and the working condition, it will be in working condition next day. So that probability is P. Of course, there is a probability 1 minus P that the repairing could not be done on nth day itself. So at the beginning of next day also, it would be in state 0.
So basically at the start of n+1 day, it will be in state 1 with probability P and state 0 with probability 1 minus P.
Yes, yes, correctly, precisely. That's right.
Okay.
And similarly, the other way around. If the machine is in good condition at the beginning of nth day, during that day it could break down and it could be in state 0 at n+1th day. Of course, a good machine has a chance 1 minus q probability of being in working condition next day also. So if by x sub n, we denote the status of the machine at the start of nth day, then the conditional probability x n plus n plus 1 is equal to 1, given xn equal to 0 is p, and the probability x n plus 1 equal to 0, given xn equal to 1 is q. So that is the information given in these two small paragraphs. Of course, P being fairly high and Q being fairly low would be the ideal kind of situation, desirable situation. The chances of breakdown is small and the chances of it getting repaired in a single day is high. Note it down if you want. Okay. Another situation. This again, of course, yeah, situation from some kind of a commercial activities in some sense, or engineering activity, qualities. So let x sub n denote the quality of nth item produced in a production system. So items are being produced on mass scale perhaps. And it can be in a good state or defective state. So xn is in state 0 means it is in good state. If it is defective, that is denoted by xn being in state 1. So if a defective item is produced, immediately some correction mechanism is sets in. And also from practice, a Markovian assumption seems to be reasonable. So the correction mechanism might start working immediately. And then if the nth item is observed to be defective, there is a good chance of, or rather there is some chance, probability Q, of the next item being good. And in a similar fashion, if the nth item is good, there is a chance that the next item, n plus 1th item, being bad is, or not even not up to the mark, is little p. So this is another situation where such a model can arise.
So sir, in an ideal situation, in a desired situation, we will want Q to be high and P to be low, right?
Correct.
So it is some sort of converse to the previous one. There P was high and Q was low.
Yes. That is because what we have declared as good and defective is in some sense other around.
Yeah, kind of converts. Yeah.
Yeah.
Kind
And
of.
the reason for this, that declaring state being in state 1 is defective means, supposing you add up these xn's, then the sum will denote the number of defective items. So that's a kind of convenience in setting up this kind of notation. If you do it in such a way. Please note it down. So the next model is a kind of classical model. It is called the gambler's ruin model. So this is an example of a simple random walk with one absorbing boundary. So a gambler with a certain initial capital makes a series of bets against an infinitely rich adversary. The infinitely rich adversary could be the casino or something like that. So the gambler has probability P of winning any particular bet and probability 1 minus P of losing any particular bet. So if he wins a particular bet, he gets 1 rupee extra that adds to his capital, initial capital. And if he loses, that costs him 1 rupee. So we denote by X sub n the gambler's wealth at the end of nth trial. So in many of these models and situations, this kind of a thing is important. End or beginning or just before certain thing is happening and so on. Because choosing it that way makes the thing convenient for modeling purposes. That is, it can fit into certain the Markov chain model or something like that. So it becomes tractable through using our whatever little bit of probability or mathematics we may know. So the bets are assumed to be independent of each other. Note it down if you want. I'll go to the next slide. So in this case, S is 0, 1, 2, etc., etc. Of course, if that gambler has some initial capital, which will generally be, I suppose, a non-negative, strictly positive number. So this case, sorry, not let, Pij is little p, that is his capital goes up by 1 unit That is, if he wins that particular bet. So Pij equal to little p if j is equal to I plus 1 for any I greater than or equal to 1, which means if he comes with at least some money in his pocket. And it is 1 minus p if j is I minus 1, again if I is greater than or equal to 1. And in one step, by one bet, he either goes to plus 1, I mean I plus 1 or I minus 1. No other possibility is, no other this thing is possible, transition is possible. So Pij is equal to 0 if j is neither I plus 1 nor I minus 1 for any I greater than or equal to 1. P00 is 1. So that is, if his capital becomes 0, then he can no longer, he becomes ineligible to bet. So P00 is 1. And P0j is 0 for any other j greater than 0. Or j different from 0. So the series of bets continues till the gambler is ruined. That is when his capital becomes 0. That's an absorbing point. Please note it down. Okay, we'll go to the next slide. So this is again a very classical model. So this is called Ehrenfest earn model.
Sir, I have a question. Can you go to the previous slide?
Yeah.
So here in this gambler's ruin model, is there any way to calculate the probability that he will be ruined at some point of time?
Yes, we will see all those things.
Okay.
This will be kind of probability of absorption. We will derive certain things and so on. Okay. Yeah, I understand. That's a kind of natural question. And the purpose is to sort of proceed towards such things, how to do that. Before that, we may also have to introduce certain concepts and so on. I mean, if a subject is being taught in a course like this, the subject will have enough jargon of its own. So you be sort of should expect such things. All right. Anyway, good question, but yeah. Suppose a total of 2D balls are distributed in 2 boxes marked 1 and 2. At the end of this this particular example, I will sort of indicate a situation where this kind of a thing arises. That will give you a good picture. So initially, some of the balls are in box 1 and the others in box 2. So at each step, one ball is drawn at random. That is from among these 2D balls. So with equal probability. So the probability of any particular ball getting picked up is 1 over 2 times t. And the ball which is removed is moved to the other box. If you take the ball out from box 2, then immediately it is transferred to box 1 or vice versa. So these steps are repeated. I mean, at this point, it looks like some kind of a marble game played by small children. They remove all the marbles from one box to another. And 2 or 3 year old kids sometimes. But then here, one introduces certain randomness. Okay. So the total number of balls does not change at any step. So X sub n, let us denote by X sub n the number of balls in box 1 at the end of nth step. Then you automatically know the number of balls in this box 2 at the end of nth step. So it is easily seen that this xn is a random variable taking only finitely many values, and the values range between 0 and 2 times t. So the state space is 0, 1, 2 up to 2 times t. Note it down if you want. Okay, we'll go to the next slide. So in this case, the transition probabilities are given by Pij, that is Pii plus 1. Pii plus 1 means what is the, it corresponds to the event that there are I balls in box 1, and in the next step, it becomes I plus 1. So if one step, the number has to increase by 1, which means the ball should have been chosen from the other box. And in the other box, box 2, at the ith step, there are 2d minus I balls because I balls are in box 1. Therefore, Pii plus 1 is 2d minus I divided by 2d. Of course, all these things assuming that there is at least one ball in box 1 at the end of nth step. And in similar fashion, if the number gets depleted by 1 in the nth step, that means the ball must have been chosen from the box 1 itself, and it would be transferred to the other one. So Pii minus 1 is I divided by 2 times t. There is no other possibility. Of course, you please check carefully that these expressions are valid at the endpoints also, at 0 as well as 2 times t. Of course, as this thing, we will assume that it is a Markov chain. But in this case, it is not really necessary to assume it can be derived. I will just indicate the next slide. So please note it down if you want to, especially these expressions. Okay. So in this case, the Markov property can actually be proved. So using this this equation, I mean, this which we have denoted by club suit, one can easily see.
Sir, can you go to the previous slide once again? Previous slide.
Yeah.
Yes, it is fine. Fine.
Okay. So using that, one can easily see that probability x2 equal to I plus 1 given x0 equal to I minus 1 and x1 equal to I. That is the past history, including the present you are given. So given that, one can easily show this probability is same thing as probability x2 equal to I plus 1 given x1 equal to I. So this becomes irrelevant. So this is the Markov property. And the next equation, again, it is the time homogeneity. And similarly here. So these two can. So once you have that, then using induction and a lengthy argument, you can establish Markov property in this model. It is not. Conceptually, it is not difficult. Because you have fairly explicit and nice expressions for PIJs. Note it down. So note that the states 0 and D are reflecting boundaries. That is, if all the balls are in one box at a particular stage, the next stage, at least the ball should go to the chosen ball must come from that box and go to the other box. Note it down if you want. We'll go to the next slide. So what appeared to us like a marble game for small kids, actually that model has come from physics. So
can you go to the previous slide? Okay, fine.
That model has come from physics due to two statistical people working in, a couple working in statistical physics, P. Ehrenfest and E. Ehrenfest. They are from Holland. So an interpretation for this is to give you a kind of toy model to sort of study the phenomenon of diffusion through a membrane. So assume that there is a fixed number of molecules in a box, and the box consists of two parts. And the two parts are separated by a membrane. Or I think perhaps this might be called semi-permeable membrane or something like that. So through that membrane, a molecule can go into the other part. Also, we make our assumption that time, the unit of time is so chosen that in 1 unit of time, just one particle goes into the other particle. So note that at any instant of time, there will be a greater tendency for drift from that part which has more balls to the part which has less balls, from higher concentration to lower concentration. You can expect a kind of a flow. I mean, the extreme situation, if all the balls are in one particular part, then the next stage, one ball should go to the empty part. So that's also clear from our expression. If sort of I exceeds D, then this probability would be greater than this. That is, if D is the half the number of particles. So if more than half the number are in box 1, then on the next step, there is a greater chance of that chosen ball coming from box 1 and going into box 2. So this will be higher. And similarly with other ways. So these things sort of stand to common sense. So this model has been found to be a fairly realistic model when there is no interaction among the particles. That is, the particles among themselves should not interact, either chemically or physically also, in the sense that if they are too crowded, then they collide with each other and that might destroy this kind of movement or may skew this movement. And this kind of a thing is supposed to be quite realistic when one considers what physicists call dilute gas. I think dilute gas, if I have understood it correctly, is a situation when the Boyle's law, etc., which you have studied, holds fairly well. Some of your physics friends may be able to explain it better. Please note it down if you want. Okay, next model. This is an inventory model. It is coming from sort of, you can say, economics. So a commodity is stocked in order to satisfy a continuing demand. There is some item, maybe grains or maybe some given electronic machines, laptops or mobiles, and so on. So let us just assume that replenishment of stock takes place at the end of periods n, maybe at the end of the day or something like that. Okay. Or sometimes it might be done only once a week. So end of the first week, end of the second week, and things like that. So one day we denote by xi sub n the aggregate demand for the commodity during the period n. That is during the entire period, whatever has been the demand for that. That is how many people ask for that particular commodity. For n greater than or equal to 1. And x0 is the initial stock. So x sub n is the stock at the end of period. See, we consider the thing this at the end of period 1, at the end of period n, but just prior to restocking. Okay. So let us say at the end of the period, depending on how much stock is at hand in that commodity or in that warehouse or in the shop, they will restock. And just before restocking, one notes down the stock, that is xn. And one assumes here xi1, xi2, xi3, that is these aggregate demands over the different periods, they are all IID, non-negative integer valued random variables. So they are independent, identically distributed, and taking values in integers. And we denote by T sub k the probability xi equal to k, which is of course, since these are IIDs, same thing as probability xi1 equal to k, k running over 0, 1, 2, etc. So these pk's are numbers between 0 and 1, and summation pk over k is 1.
Sir, I have a question. So why probability xi equal to k equals to probability xi1 equal to k? Xi1 and xi.
IID, identically distributed.
Okay, so they have the same distribution. Okay.
Yes, IID, I thought you knew the notation for that. Independent, identically distributed random variables. Okay, R dot V is the abbreviation for random variables. IID stands for independent, identically distributed. I thought you might have seen this kind of abbreviation in your previous course.
Okay.
Recall when you must have studied strong law of large numbers, weak law of large numbers, central limit theorem, many things. This notation will be used, IIDs. See, generally, I mean, Markov chains, Markov process are nice to study, but while doing your course, Markovian nature is not advisable, right? You should remember what has been done earlier. The stock levels are examined at the end of each period. Okay, let me go to the next slide. See, in these things, the restocking, how to do that? There is always a policy which is adopted by the, let's say, the businessman in this case, or a manufacturer. So, two integers little s and capital S are chosen beforehand by the person or the businessman. So these are, for our this thing, these are two integers which are prescribed. Of course, capital S will be strictly non-negative. Of course, little s can be 0. But very often, little s also will be strictly positive. So these are known constants. So you can assume that this capital S is a kind of storage capacity. See, commodity stocked means commodity has to be stored in some place. Even if the thing is for a single day or something like that, or if for the period we are considering is a week-long period, then the shop or the warehouse or showroom, whatever it is, things have to be stored. And the storing that there will be a capacity, finite capacity for these things. So this capital S would be governed by perhaps that capacity. So if the end of period stock, that is just prior to restocking, if that level, I mean, if the number of commodity on hand are available there is less than or equal to this little s, then the shopkeeper or the businessman thinks that perhaps because of past knowledge, past experience, and so on, he should at least restock at that stage. He should restock. So while restocking, he increases the stock level to the maximum possible capacity. So if the end of period stock just before restocking is less than or equal to S, then an amount sufficient to increase the quantity of stock on hand to level S is immediately procured. Of course, one implicitly assumes that this procuring this much, there is no problem. Wherever it is coming from, let's say they have almost infinite this thing.
So basically, at least capital S minus small s is restocked.
Just a second. Yeah, sure. Yeah, at least that much is there at the beginning of any period. I mean, that next period. Okay, just wait. We are not. So if the level of that stock at the end of that period is greater than S, then nothing is procured. Because if it remains in this thing without being sold, then there will be waste. So he doesn't want to increase the stock beyond that. So this is the kind of maximum possible that commodity can store. And this is the kind of minimum level below which he doesn't want to go. He doesn't want the stock to fall. And if it exceeds little less, then he will wait for how is the thing business next day and so on. So if by experience, he might have known that only once in 3 or 4 days, he needs to do replenishment. Okay. So now, this stock on hand, etc., also depend on the demand. Suppose in a particular day, the demand is rather huge. then the stock on hand can be considered negative in the sense that to accommodate for unfulfilled demand. Say this less than or equal to yes, it also includes the possibility the end of period stock can even be negative. So the state process of the state of the process xn varies over yes, s minus 1, s minus 2, 0, then minus 1, minus 2, etc. Here, negative value is interpreted as an unfulfilled demand that would be satisfied immediately upon restock. So to go back to the preceding slide, if this is less than yes and it is a negative number, let us say it is minus 10 and yes is 100, he will procure 110 units so that this stock can be raised to 100, and also that 10 people whose demand could not be fulfilled, they also can be taken care of.
But sir, how can the stock can go below 0?
No. It is stock below 0 means in your book. Let us say this little yes is 10. Okay.
Yes.
And all the things are rather, it is midway between something. And all the, let us say that there is, at the end of the day, there are 30 items available. Okay. Little s is 10, let us say. Okay. But about 40 customers come, they want it. So 30 people he can satisfy. But the remaining 10, he will tell them when the thing comes, I will give you.
Okay.
Okay. Especially in these days of mailing, mail order and various things like that, that is easily comprehensible.
Okay, then the state will go to minus 10.
Yes.
Okay.
So minus 10, let's say as soon as that stock which raises up to level S comes, this man will take care of those 10 people who could not get when they came to the shop or when they rang up and asked for it. Okay. I mean, even in the old days of, or even now, somebody physically going to the shop and asking, he might just say that we are run out of stock. Please come tomorrow early morning itself, sir. We can take care of your order. He keeps it aside for those customers who could not be satisfied the preceding day. And the next day, if they come, he will give it. And also making sure that he has enough stock to take care of the demands on the N+1 of the day. So the state of the process xn varies over this. And a negative value is interpreted as an unfulfilled demand that would be satisfied immediately upon restocking. So according to the replenishment policy, which we had seen in the previous slide, so if at the end of the day thing is between S and little s and capital S, that stock on hand at the end of next day before restocking would be xn minus xi n+1. So xi n plus 1 is the demand during the n plus 1th day. And whatever was there at the previous, this thing, that early morning of that day, that will try to satisfy that. And if xn happens to go below s, then xn plus 1 would be, because at the beginning of the day, there will be s items available, capital S. S minus xi sub n plus 1. And here again, we assume xn to be a Markov chain, but since this xi is are IID random variables, this can actually be proved. And the state space is what we have given here. S, S minus 1, S minus 2, etc. Note it down. We will go to the next slide. This is the last one for today. So the transition probabilities are P sub ij, that is probability of xn plus 1 equal to j given xn equal to I. So you go to this expression, from that you can easily find out. Then this is the probability xi n plus 1 equal to I minus j. That is P sub I minus j. So if this I happens to be between little s and capital S. And similarly, if this is strict, less than or equal to little s, then this probability is xi n plus 1, probability xi n plus 1 is equal to s minus j, that is P sub capital S minus j. So here, note that the xn plus 1 equal to j, the j can possibly be negative. So that can arise if, in the second case, if xi n plus 1 is strictly bigger than s. So if j happens to be negative, this I minus j would be a positive number. And similarly, if xi n plus 1 exceeds xn also in this case, in such a case, then this again, the j can be negative. Okay, we'll stop here for the day. Please note it down if you want to, or if you want me to go over any of the previous slides, please tell me. Okay, I'll stop sharing. And so we will end the session for today. And take care, and we meet again. Yes?
Yes, sir. Can you show the last slide once again?
Wait. Yeah.
Only the last slide.
I think this is the last slide, right?
But I am not able to see.
Oh, I have not shared.
No, you're not sharing screen.
Yes. Okay. Now you have to bear with me. Now, let me. All right. If the sequence gets sort of Now can you see?
Yeah.
Okay. Succeeded.
Okay, sir. Okay, sir. Fine.
Okay. So we will end the session and take care. Meet on Monday. Okay. Have a good weekend. End meeting for all.